What if I told you that right now, wherever you are sitting, there is something all around you that is 6 times more abundant than the matter that makes up your own body? Something that surrounds you and passes through you every single second, yet you cannot see it, feel it, or collide with it. It allows light to pass straight through it, meaning it cannot even create a shadow. It does not respond to our instruments. It does not block the ground beneath you, and it does not disturb the air around you. Yet it exists. It is everywhere. It is spread throughout the entire universe. And the most astonishing part is that for the last 92 years, scientists around the world have been searching for it. Every underground laboratory, every particle accelerator, every powerful telescope has looked for a sign of it. But all of them have remained empty. Not a single piece of direct evidence has been found. A mystery that has lasted for 92 years. Then, on November 25, 2025, a scientist from Japan published a paper that captured the attention of the scientific world. The research suggested a signal coming from the center of the Milky Way that had never been observed before. A shape appearing like a faint, glowing, ghostly halo. A pattern that matched what the theory had predicted decades earlier. Was this the first glimpse of this invisible substance that humanity had been searching for? Or was it just another false hope, like many possibilities that came before it? This is the story of the universe's greatest mystery. Something that exists all around us, but remains invisible. A cosmic cold case that has lasted for 92 years. The story of a scientist who was ignored for 40 years, mocked with a nickname Spherical, and yet eventually turned out to be pointing in the right direction. This is the story of dark matter. The story begins in 1933 at the California Institute of Technology. There was a 35-year-old Swiss scientist named Fritz Zwicky, a man with a personality that made him both respected and controversial. His colleagues often found him difficult because when someone disagreed with his ideas, he had a habit of calling them spherical. When people asked what he meant by that, he explained, "A spherical person looks the same from every angle." In other words, there was no perspective from which that person appeared impressive. His unusual attitude often frustrated the scientific community, but Zwicky's mind worked in a completely different way. That same year, he was studying observations from the Mount Wilson Observatory. This was the same telescope that Edwin Hubble had used years earlier to discover that the universe was expanding. Zwicky was studying a massive collection of galaxies known as the Coma Cluster. It was a gigantic group containing around 1,000 galaxies, located about 320 million light-years away from Earth. Zwicky did something that no one had attempted before. He measured the speeds of different galaxies inside this cluster, one after another. What he discovered was astonishing. The difference in their speeds reached around 2,000 kilometers per second. Think about it this way. To keep a galaxy cluster together, you need gravity. Gravity comes from mass. More mass creates stronger gravity, and stronger gravity creates a greater force holding everything together. But Zwicky calculated that if the visible matter, the stars, and gas we could actually see was the cluster's entire mass, then the gravity should not have been strong enough to hold it together. Those galaxies should have been flying apart. The cluster should have scattered billions of years ago. Yet it was still there. 1,000 galaxies remained connected, held together by something unseen. After completing his calculations, Zwicky reached a remarkable conclusion. The Coma Cluster had to contain around 10 times more mass than the visible matter could explain. But that missing mass was nowhere to be found. He gave this mysterious substance a German name, Dunkel Materie, meaning dark matter, a type of matter that exists but cannot be seen, while its gravity continues to influence the universe around it. It was the reason the cluster was not breaking apart. When Zwicky published his research, the reaction from the scientific community was almost nothing. He was ignored. Many scientists believed his measurements were incorrect, that there were mistakes in his calculations, or that he was simply making another exaggerated claim. They saw him as an eccentric Swiss scientist, known for making dramatic statements. And during this period of silence and rejection, 40 years passed, a full 4 decades. Zwicky continued working on his ideas throughout his life. He published hundreds of scientific papers, but the world was not ready to listen. Then, in 1970, an astronomer named Vera Rubin entered the story. Vera approached the mystery from a completely different direction. Instead of studying galaxy clusters, she studied individual galaxies. She measured the rotation speeds of 60 galaxies, examining how quickly stars moved near the center of galaxies compared with those located farther away at the edges. The physics seemed simple. Look at our own solar system. Mercury is closest to the Sun, and because of that, it moves around the Sun faster than the planets farther away. Neptune is the farthest planet from the Sun, and it moves around its orbit the slowest. Why? Because gravity is strongest near the center and becomes weaker as you move farther away. The same principle should have applied to galaxies as well. Stars near the center should have been moving faster, while stars at the outer edges should have been moving slower. But Vera discovered something completely unexpected. The stars at the edges of galaxies were rotating just as quickly as the stars near the center. Something else had to be providing additional gravity to keep those stars from escaping. In other words, these galaxies contained far more mass than the visible matter could explain. Exactly what had been predicted 40 years earlier. Vera Rubin's data finally forced the scientific community to take the idea seriously. 60 galaxies, 60 different locations, yet the same pattern appeared again and again. This was not a coincidence. It meant that Zwicky was right, and when scientists added everything together, the result was astonishing. Only about 15% of the matter in the universe is visible. The remaining 85% is dark. This means that stars, planets, gas, dust, you and me, everything we can see and touch, make up only a small fraction of the universe's matter. The other 85% is something completely unknown. And this is one of the most difficult ideas for the human mind to accept. We have proven that something is there, yet even after decades of searching, we still do not know what it actually is. Our entire understanding of the universe is built on a mystery. So scientists began the search. Over the last 50 years, dark matter detection experiments have been created in different parts of the world. Deep beneath a mountain in Italy sits the Gran Sasso Underground Laboratory, protected from cosmic rays that could interfere with sensitive measurements. In South Dakota, the LUX experiment was built around a massive tank filled with liquid xenon, designed to detect the rare moments when dark matter might interact with normal matter. And in Switzerland, the Large Hadron Collider at CERN became the most powerful particle accelerator ever built, searching for clues that could reveal the hidden particles of the universe. Every detector was built around the same idea. If dark matter is made of particles, and if those particles occasionally interact weakly with ordinary matter, then these experiments might capture that rare event. But after 50 years, nothing appeared. Every detector remained silent. Every experiment reached the same disappointing conclusion. No direct evidence had been found. So, what exactly is dark matter? Scientists have proposed several possibilities, but 2 ideas have remained among the leading theories. The first is WIMPs, which stands for Weakly Interacting Massive Particles. These particles were predicted by theories such as supersymmetry, an extension of the standard model of particle physics. The second possibility is axions, extremely lightweight particles that could also explain the missing matter in the universe. But today the focus is on WIMPs, because the discovery reported in November 2025 is connected to this idea. To understand WIMPs, we first need to understand an interesting property of nature. Every particle has a corresponding partner called an antiparticle. The antiparticle of an electron is a positron, which is almost identical to an electron but carries the opposite charge. The antiparticle of a proton is an antiproton. This is not science fiction. Antimatter is real. Even an ordinary banana sitting in your kitchen releases a positron approximately every 75 minutes. When a particle meets its antiparticle, something extraordinary happens. They both disappear completely. Their mass is transformed into energy, and that energy is released as radiation, mainly in the form of gamma rays. This is the meaning behind Einstein's famous equation, E equals mc squared. Mass and energy are connected. They are two different forms of the same thing. Annihilation is one of the clearest examples of this relationship. Matter is converted into energy, leaving behind only radiation. The theory suggests that WIMPs could behave in a similar way. When two WIMPs meet, they would annihilate each other and release gamma rays. The energy of those gamma rays would appear at a specific level, depending on the mass of the WIMPs themselves. So if WIMPs truly exist and make up dark matter, then regions containing large amounts of dark matter should also contain more annihilation events. And more annihilation events should produce more gamma rays. This means scientists should search for these signals in places like galactic halos, where dark matter is believed to be concentrated. But there is a major problem. Galaxies are already filled with many sources of gamma rays. They can come from exploding stars, black hole accretion disks, pulsars, magnetic objects, and extremely hot clouds of gas. So even if a dark matter signal exists, it could easily be hidden beneath all of this cosmic noise. It is like trying to identify a single fingerprint at a crime scene where fingerprints from 100 different people are already covering every surface. You are searching for one specific mark, but separating it from everything else becomes incredibly difficult. And this is where Tomonori Totani enters the story. Totani is a Japanese astrophysicist and a professor in the Department of Astronomy at the University of Tokyo. In early 2024, he began working on a problem that few others were approaching in the same way. There is a NASA telescope called the Fermi Gamma Ray Space Telescope, which was launched in 2008. It scans the entire sky continuously, completing a full survey approximately every 3 hours. This meant Fermi had collected 15 years of gamma ray observations, data covering every region of the sky, creating a new snapshot every 3 hours. Totani began examining that enormous amount of data, but he approached it in a very specific way. First, he removed the center of the Milky Way from his analysis. The reason was simple. The galactic center is extremely bright in gamma rays. There is so much activity happening there that even a faint signal from dark matter would easily disappear beneath all the noise. So instead, he focused on the halo region, the vast spherical area surrounding the main disk of the galaxy, where theories suggest dark matter should be concentrated. Then began the most difficult part of the process. For 18 months, the team carefully identified every known source of gamma rays, removed their signals from the data, and examined what remained. Supernova remnants, pulsars, black hole accretion disks, magnetars, and every other known source were studied and subtracted one by one. And what remained was something unexpected, a gamma ray pattern. The shape matched what scientists had predicted for a dark matter halo, a faint, ghostly sphere extending around the Milky Way. But the shape was not the only thing that matched. The energy pattern matched as well. The gamma rays showed a peak at around 20 giga-electron-volts, or 20 GeV. This was the exact energy range predicted if WIMPs had a mass approximately 500 times greater than a proton. The shape matched, the energy matched, the distribution matched. Everything appeared to point in the same direction. Totani published his paper on November 25, 2025, in the Journal of Cosmology and Astroparticle Physics. And he made a statement that immediately captured attention. He said that if the results were correct, then, to his knowledge, this would be the first time humanity had directly observed dark matter. From Zwicky's prediction in 1933 through 92 years of mystery and 50 years of unsuccessful experiments, humanity may have finally reached the moment of its first glimpse of this invisible substance. But then came the uncertainty. The scientific community was not completely convinced. Soon after the paper was released, researchers began discussing their concerns. Some pointed out that this was not the first time scientists had claimed to discover unusual patterns in Fermi telescope data. In previous cases, those signals eventually turned out to come from ordinary astrophysical sources, Others argued that there were still unanswered questions in Totani's method of analysis. But the most important objection was related to WIMPs themselves. According to current theories, WIMPs would have formed shortly after the Big Bang, when the universe was still extremely young. Scientists can estimate how much dark matter should exist by studying the cosmic microwave background. The ancient radiation left over from the early universe, often described as a baby picture of the cosmos. The amount of WIMPs predicted from this early universe measurement does not appear sufficient to create a gamma-ray signal as strong as the one Totani detected. This means the signal could be real, but it may not necessarily be caused by WIMPs. Perhaps it comes from another type of unknown particle, or perhaps it is produced by an astrophysical source that scientists have not discovered yet. Professor Carlos Frank, one of the scientists who helped develop modern WIMP theories and has spent decades studying dark matter, made a remarkable comparison. He said that discovering dark matter would be as significant as Darwin's discovery of the theory of evolution. A statement like that is not made lightly. It is something scientists only say when the evidence reaches an extraordinary level of certainty. Because the future of physics and our understanding of the universe depend on this mystery being solved. So what happens next? If WIMPs truly are dark matter, and if they are producing gamma rays through annihilation inside the Milky Way's halo, then the same process should also be happening in the small satellite galaxies that orbit our galaxy. These dwarf galaxies contain very little ordinary matter, but are believed to be extremely rich in dark matter. If scientists detect the same 20 GeV gamma ray signal coming from those galaxies as well, the evidence would become much stronger. Totani himself has suggested that this is the next important test, and this is where a new instrument enters the story: the Vera C. Rubin Observatory. It carries the name of the same Vera Rubin, whose observations helped confirm Zwicky's dark matter theory decades earlier. The observatory began operations in Chile in June 2025. Each night it captures hundreds of images of the sky and produces around 20 terabytes of data. That is roughly the amount of storage contained in dozens of smartphones, created every single night. Over the next 10 years, it is expected to produce around 60 petabytes of data, equal to 60 million gigabytes. Hidden inside this enormous collection of observations could be discoveries that humanity has never seen before. Perhaps the next important signal will come from dwarf galaxies. Perhaps Totani's interpretation will be confirmed. Or perhaps future observations will show that the signal came from something completely different. For now, the mystery remains open. Maybe humanity has finally seen dark matter for the first time. Or maybe we are still searching for the answer. The coming years will reveal what is truly hiding in the darkness of the universe. But one thing remains clear. Around 85% of the matter in the universe is still hidden from us. We understand only about 15%, and yet everything we see depends on that unseen majority. Galaxies are held together by the gravity of dark matter. The first stars that formed after the Big Bang are believed to have formed within the gravitational structures created by dark matter. The universe, as we know it, including our own existence, is connected to something we still cannot directly see. And 92 years ago, a Swiss scientist told the world that something like this had to exist. But he was ignored. He was dismissed. He even responded to those who opposed him by calling them spherical bastards. Yet, in the end, his idea pointed toward the truth. So remember what we talked about at the beginning. There is something around you, something passing through you, something that is about 6 times more abundant than the matter that makes up your own body. Now you know its name. It is Zwicky's Dunkel Materie. Dark matter. Even after 92 years, it continues to hide from us. But in 2025, perhaps humanity finally caught a glimpse of its shadow for the very first time. And that leaves us with one question. If you had been in Zwicky's position in 1933, knowing that your idea might be ignored for 40 years, knowing that you might never live to see the world accept your discovery, would you still have published that paper? Would you have stood alone with your theory while the entire scientific community disagreed with you? A single idea, a single calculation, A single person willing to question what everyone else believed. That is often where the greatest discoveries begin, because sometimes the universe reveals its secrets slowly, and sometimes the first person to see the truth has to wait decades before anyone else can see it too.